The solar interior. Nuclear fusion reactions at the center of the Sun produce gamma-ray photons with energies of about 1 megaelectronvolts, 10 to 6 electron volts. By contrast, what we see emanating from the Sun's surface are visible light photons with wavelengths of about 500 nanometers. A simple model that explains this difference in wavelength is that a photon undergoes Compton scattering many times. In fact, about 10 to 26 times as suggested by models of the solar interior as it travels from the center of the Sun to its surface. Part A. Estimate the increase in wavelength of a photon in an average Compton scattering event. Okay, so the energy of gamma ray photons are given as E is equal to 1 mega electron volts. And that's equal to 1243 electron volt nanometers divided by lambda in nanometers, and this is equal to hc over lambda, Planck's constant times speed of light divided by the wavelength. Okay, so we can calculate the wavelength of the gamma ray photons. Lambda is equal to 1243 divided by 1 times 10 to 6 electron volts. So this gives us 1.243 times 10 to minus 3 nanometers. And that's actually what we call roughly 1 picometer. So that's the wavelength of the gamma rays. Now, what we see emanating from the surface of the Sun is the visible light. So the change in the wavelength is a final wavelength 500 nanometers, initial wavelength 1.243 10 to minus 3 nanometers. So that number is negligible compared to 500. Therefore, the wavelength change is about 500 nanometers. And we have 10 to 26 Compton scattering events in which this wavelength change occurs. So per event, how much is the wavelength change? We can calculate delta lambda per event is the total wavelength change, delta lambda prime, divided by number of Compton scattering events, 10 to 26. So this gives us 5 times 10 to minus 7 meters divided by 10 to 26. So we find that the wavelength change per scattering event is 5 times 10 to minus 33 meters per event. Okay, so that answers part A of the problem. Part B, find the angle in degrees through which the photon is scattered in the scattering event described in part A. Hint, useful approximation for cosine phi is 1 minus phi squared over 2, which is valid for phi much less than 1. Note that phi is in radians in this expression. Okay. Now, we have our Compton scattering expression. The change in the wavelength, delta lambda, is equal to h divided by mc, 1 minus cosine phi, where phi is the scattering angle. And for phi very small, so this is something we have discussed in the lecture, remember. We have derived this Compton scattering formula. For phi very small, we can estimate cosine phi as 1 minus phi squared over 2. This is the Taylor series expansion around phi is equal to 0. And here I want to note that mass of an electron is rest mass 9.11 10 to minus 31 kilograms. And for the speed of light, we're using 3 times 10 to 8 meters per second inside the sun. Okay, so the change in wavelength per scattering event is approximately h divided by mass of the electron times the speed of light, 1 minus 1 plus phi squared divided by 2, and these ones will cancel out. And so we will find that the change in wavelength, delta lambda, is approximately hc divided by mc square, the rest energy, times phi square, which means the scattering angle phi for this electron-photon scattering event can be calculated as because we have a factor of 2 here, 2 delta lambda mc divided by h to the power 1/2. That's the scattering angle. Now, if I calculate this, phi is equal to 2 times delta lambda, 500 nanometers, 5 times 10 to minus 33 meters per scattering event, 5 times 10 to minus 33. Mass of the electron, 9.11 10 to minus 31 kilograms. Speed of light, 3 times 10 to 8 meters per second, divided by Planck's constant, 6.63 10 to minus 34 joule seconds, all to the power 1/2, gives us, for the scattering angle phi is equal to 6.4 times 10 to minus 11 radians. Okay, so that's a rather small scattering angle. And in part C, it is estimated that a photon takes about 10 to 6 years to travel from the core to the surface of the sun. Find the average distance that light can travel within the interior of the sun without being scattered. This distance is roughly equivalent to how far you could see if you were inside the sun and could survive the extreme temperatures there, as your answer shows the interior of the sun is very opaque. It takes a delta T of 10 to 6 years for a photon to travel from the interior of the sun to the outside surface. So that is 10 to 6 years. 1 year is 365 days. 1 day is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds. So this gives us a total of 3.15 times 10 to 13 seconds. For the speed of light in the sun, we're using the speed of light in vacuum, which is c 3 times 10 to 8 meters per second. The average time between collisions, between Compton scattering events, that's the time a photon has before it scatters, it goes through the next scattering event. Let's call this tau. This is delta t, 10 to 6 years, and we have a total of 10 to 26 scattering events. So we have 3.15 times 10 to 13 seconds divided by 10 to 26. So this gives us a tau of 3.15 times 10 to minus 13 seconds. So that's the average time between collisions. The speed of light is the distance the photon travels without colliding, the mean free path divided by the average time between collisions. L is mean distance traveled between collisions. Okay, so this distance is the speed of light times tau, which means it is 3 times 10 to 8 meters per second times the mean free time, 3.15 10 to minus 13 seconds. That gives us 9.4 times 10 to minus 5 meters. So that's our viewing distance inside the sun, 9.4 times 10 to minus 5 meters. That's a very small number. It's a very small viewing distance. That's why we say inside the sun it's opaque, it's not transparent. We have a very small viewing distance. Okay, so in this problem, we have nuclear fusion reactions taking place at the center of the sun, producing gamma ray photons with 1 mega eV energy. But what we see at the surface is mostly visible light photons, 500 nanometers wavelength. So how come these gamma ray photons turn into these visible photons? The reason is that the photons undergo Compton scattering events many times, about 10 to 26 times, before it reaches the surface of the sun. So what is the increase in the wavelength of a photon in an average Compton scattering event? The gamma ray photons have a wavelength of 1 picometer. That's what we see from E is equal to hc over lambda. And the change in wavelength is about 500 nanometers. And we have 10 to 26 Compton scattering events. So change in wavelength per Compton scattering event is 5 times 10 to minus 33 meters. Now this happens for a scattering angle phi, h over mc equals 1 minus cosine phi. So we have, from this calculation, if phi is very small, we can substitute 1 minus phi squared over 2. We see that the scattering angle phi for these photons is very small, 6.4 10 to minus 11 radians. Now, it's going to take a photon to reach the surface 10 to 6 years, coming from the core of the sun, and the speed of light in the sun is given. The average time between collisions is the time spent within the interior of the sun divided by the number of scattering events, 3.15 10 to minus 13 seconds. And because the photons travel a mean distance of L in a mean free time tau between successive collisions, L is equal to c times tau, we find that L is 9.4 10 to minus 5 meters, or we can say this is 94 10 to minus 6, so 94 micrometers. It's a very, very small viewing distance, and that leads us to the conclusion that the interior of the sun is very opaque.